This talk is about planning and learning in partially observable systems via filter stability. The basic model that we're going to consider is that of a partially observable Markov decision process, which I'll start by motivating. At a high level, our goal is reinforcement learning. There is some agent that gets to interact with the environment by taking actions, and it receives state information and rewards at every step. And the goal of the agent is to learn a policy that maximizes rewards. The standard model for this is a Markov decision process, which we abbreviate as an MDP. Basically, a Markov decision process is a controlled version of a Markov chain. There's some state space and some initial state or initial state distribution. There's some space of actions that the agent can take. For every state and every action, there's some reward associated. And there are some transition probabilities associated for the next state, given the current state in action. And finally, there is some finite horizon H. So the agent will start at some state, take some action, receive some reward, transition stochastically to a new state, and proceed H times. The goal is to find a policy that's a mapping from states to actions that maximizes the expected reward received by the agent from the environment. There's two main problems associated with MDPs. One of them is the planning problem. Given a full description of the MDP, including the transitions, the rewards, and so forth, compute an optimal or near optimal policy. The second harder problem is learning, where the algorithm only is allowed to access the MDP by interacting with the environment in some fashion. And the goal is, again, to learn an optimal or near optimal policy. Both of these problems have classical algorithms that run in time polynomial in the number of states, the number of actions in the horizon. For the learning problem, there's also the question of sample complexity, and the learning algorithms have polynomial sample complexity as well. I'll give a sketch of a simple planning algorithm for Markov decision processes because it's necessary for understanding later parts of this talk. Basically, the key idea is that the optimal policy, due to the Markovian property of the transitions, only depends on the most recent state. As a result, dynamic programming has polynomial time complexity. More formally, let's say that we let v sub h of s denote the value that the optimal policy receives when at state s at time step h. And this is well defined because the optimal policy only depends on the most recent state. Then we can actually compute v sub h based on v sub h plus 1, as well as the transitions and the rewards. And we can compute the best action to take at state h, at state s, and time h, based on the same v sub h plus 1. Essentially, we choose the action that achieves the value v sub h of s. And we do this by backwards induction from the last step to the first step. So that was a simple solution, which unfortunately is insufficient for many applications, because many applications cannot be modeled by a standard Markov decision process with a small number of states and actions. There's two possible reasons for this, two possible major reasons. One of them is that there just may be too many states to write down or visit. A second reason is that maybe the agent does not actually observe the full state. For example, in a medical setting, the doctor's actions might be based on some measurements taken of a patient, but those may not be entirely indicative of the evolution of the patient's health. And this is a model addressing this issue is a model known as partially observable MDPs. So for both of these issues, there's a rich understanding of augmented models that address the corresponding issues, and of the sample complexity required to learn in these augmented models. Unfortunately, computational complexity is much less well understood. In particular, modern theoretical reinforcement learning for augmented Markov decision processes is generally built on computationally intractable oracles that solve non-convex optimization problems to plan near optimal policies. So the focus is on optimal sample complexity for learning, but the computational complexity of planning is completely ignored. In this work, we want to change this paradigm, and we ask if there are computationally efficient algorithms with strong end-to-end guarantees, in particular in the setting of partial observability. So recall that in MDPs, the agent at every time step observes the current state. In a POMDP, there's some observation space and some emission distribution for every state. So conditioned on the current hidden state, the agent observes some random observation drawn from this emission distribution. We can think of POMDPs as a controlled analog of hidden Markov models. Again, there are two main algorithmic questions, planning and learning. And we might ask, can these problems be solved in time polynomial and all the relevant parameters? In this talk, we'll focus largely on planning and discuss learning at the very end. And note that planning is the easier problem. Unfortunately, it's still hard for POMDPs. There's a classic lower bound due to Papadimitriou and Tsiklis, which says that optimal planning in a POMDP is p-space hard. The fundamental issue is that it's not even clear how to represent an optimal policy succinctly. Recall that in MDPs, the saving grace was that an optimal action only depends on the current state. But in POMDPs, the optimal action can depend on the entire action observation history thus far. Basically, the reason is that the agent needs to know the agent's action depends on where it thinks it is in the state space. And this posterior distribution depends on all of the actions and observations so far. As a result, dynamic programming will require computing the optimal action for every possible history. And the number of possible histories is exponentially large in the horizon. This is known as the curse of history. And we're trying to avoid it. We're trying to avoid exponential time complexity in the horizon and also in the number of states. So that was all for optimal policies. We can actually show something even stronger. Under a reasonable complexity theoretic hypothesis, even near optimal policies do not have polynomial size descriptions. So this is all in the worst case with no assumptions. So we might ask, what about beyond worst case? Should real-world POMDPs have succinct descriptions of good policies? And under what assumptions can we show that this holds? Well, if we look at the computationally hard instances in the above lower bounds, they have the curious feature that the observations are completely useless. The observation distribution for one state is the same as the observation distribution from another state. So we might ask, what if the observations are at least somewhat useful? What if they leak some information about the state? Then can we get computationally efficient planning and learning? Concretely, we say that a POMDP is gamma observable for some parameter gamma that we think of as a constant between 0 and 1. If for any time step h and for any two distributions b and b prime on states, we will often refer to b and b prime as belief states. If the b and b prime are well-separated distributions on states, then they induce well-separated distributions on observations up to some factor of gamma. And here we're measuring in total variation distance. So this was actually previously introduced in a prior work for a related purpose of understanding the stability of beliefs under misspecification in hidden Markov models. The key point of this assumption, both in our work and in theirs, is that it makes no assumption on transition dynamics. And this sets our work apart from previous works on planning in POMDPs. So now we can state our main result, which is that under gamma observability, there is a quasi-polynomial time algorithm for planning. That is, given the description of the POMDP, we can compute efficiently an epsilon suboptimal policy. That is, the gap between the expected reward achieved by our policy versus the best policy is at most epsilon. In one sentence, the key technical idea is to prove that the Bayes filter in observable POMDPs is exponentially stable. Here by Bayes filter, we mean the operator that computes the posterior on states at a given time step, given the actions and observations so far and some prior and earlier time step. And we show that this stability holds regardless of transition dynamics. So it does not require any mixing properties. It only requires observability. Why is this algorithmically useful? Well, the issue with POMDPs, the curse of history, arose because the best action to take at some time step, well, it depends on the posterior on states at that time step. which in turn depends on all actions and observations so far. As a result, dynamic programming needs to consider exponentially many states. However, if we can show that the posterior approximately only depends on the most recent logarithmic number of actions and observations, then there's a near optimal action that only depends on these actions and observations. So approximate planning by dynamic programming only will take quasi-polynomial time, thus alleviating the curse of history. We also show that it's not possible to improve beyond quasi-polynomial time for general gamma observable POM-DPs, but we will not discuss this further. Back to filter stability, which we also term belief contraction. The main technical result we prove is the following. If we consider any gamma observable POM-DP and policy pi, step h, then we can consider, for some trajectory, we can consider the true posterior at time step h, which is the probability distribution of the current state given all the actions and observations seen so far. And one way this can be computed is by looking at t steps back at the distribution on states at time h minus t, and then applying the appropriate Bayes updates t times, using the intervening actions and observations from h minus t to h. Of course, this way of computing b sub t, the posterior distribution at time h, depends on everything so far, which of course is necessary. We want to show that we can approximate b sub t by some function of only the last t actions and last t observations. So we do this in that natural way. Instead of letting b sub 0 be the true distribution of the state at time h minus t, we let b prime sub 0 just be the uniform distribution over states, and then we apply the same Bayes updates t times based on the actions and observations between time step h minus t and h. Then what we claim is that in expectation over the trajectory tau, the total variation distance between b sub t, the true posterior, and b prime sub t, the approximate posterior that only depends on recent actions and observations, this decays exponentially in t. To go into the proof sketch, we need to make a bit more notation defined. So the Bayes operator is the operator that computes the posterior unstates given some prior unstates and a new observation. And its definition is written out here. The update operator computes the posterior after taking some action and seeing some new observation. And its definition is written here. Then essentially, what we are trying to show is that in expectation, the update operator is exponentially contractive. So ideally, we would like to just show that it's contractive outright. We'd like to show that for any beliefs B and B prime, any action A and any observation Y, the divergence between the posterior beliefs given the action A and observation Y is significantly less than the divergence between the prior beliefs B and B prime. And here we're using KL divergence rather than total variation distance because, as is often the case, it's easier to work with. Now, is this actually true? Well, what gives us some hope is that from the data processing inequality, applying the transition matrix T of A corresponding to action A to the beliefs B and B prime does not increase the divergence between B and B prime. Unfortunately, that's only half of the update step. The second step is incorporating the new observation. And for some observations, the Bayes operator can increase the KL divergence. So that was too strong to hope for, that the update operator is always contractive. What about in expectation? It turns out that in expectation, this is true. So in expectation, the KL divergence between the posteriors, given some observation Y, is at most the KL divergence between the priors, B and B prime, and the decrement is exactly equal to the KL divergence between the induced observation distributions, induced by B and B prime respectively. The proof is by chain rule. And now we want to ask, is this a large enough decrement? Does it imply exponential convergence? Well, using Pinsker's inequality, we can convert the decrement into the total variation distance between the induced observation distributions squared. And then using observability, we can show that that's at least gamma squared times the total variation distance between B and B prime squared. Unfortunately, now ultimately we want to show that the expected KL divergence between the posteriors is some multiplicative factor less than the KL divergence between the priors. So we need to convert the decrement into some function of the KL divergence between B and B prime, which is some sort of reverse Pinsker inequality. And even assuming that B and B prime have bounded ratio, the best we can hope to show is that the total variation distance between B and B prime is at least some constant times the KL divergence between B and B prime, which means that the decrement we can achieve is at least some constant times gamma squared times the squared KL divergence between B and B prime. And this does give some contractivity, but it's not strong enough. And this contractivity was actually a result proven in the prior work that introduced gamma observability. They showed that after T update steps, the true posterior BT and the approximate posterior B prime sub T are at most epsilon apart in KL divergence in expectation, provided that T is at least polynomial in 1 over gamma and 1 over epsilon. This was enough for their purposes of proving stability against misspecification in HMMs. But for our purposes, it is not enough, because ultimately, the suboptimality we are going to incur in our approximate policy is going to be essentially obtained by summing the error in the posteriors over all h time steps. So if we throw away epsilon reward at every time step due to this approximation error in the posterior, then we need epsilon to be much less than 1 over the horizon, at least, to get anything non-trivial in terms of suboptimality of our policy. But if epsilon is 1 over poly in the horizon, then the number of update steps T, the window of observations and actions that we need to consider to compute our approximate posterior, needs to be longer than the horizon H, which is vacuous. So we'll end up with an algorithm that's exponential in the window length T, and therefore exponential in the horizon H, which is what we're trying to avoid. So we really need exponential convergence of our approximate posterior. And we achieve this by a win-win argument. So we show that either a stronger reverse Pinsker inequality holds from the previous slide, so we can get something linear in the KL divergence as our decrement, rather than something quadratic. Unfortunately, this might not always hold. So there's a second case. In the second case, we prove that there is some anti-concentration. In particular, there is some event on the observation space where there is a sufficient decrement. Now, it might be canceled out by some event where there is an increment, so the expectation might not actually have a large decrease. However, in either case, we can show that the expected square root KL divergence has a sufficient decrement. And as a corollary, we get our exponential stability. This is not quite what we claimed in the previous theorem statement, since we have a log squared of 1 over epsilon rather than a log of 1 over epsilon. And a similar, technically similar, but much more involved argument using Rényi divergence rather than KL divergence achieves the log 1 over epsilon that we claimed previously. And by applying this belief contraction together with dynamic programming, we immediately get our main algorithmic result, which is that given the description of a gamma observable POMDP, there's a quasi-polynomial time algorithm that computes an epsilon suboptimal policy. The final question we want to mention is, what about the learning problem? So this actually turns out to be much more complicated, and it was not obtained in the paper that this talk covers. However, in subsequent work, we did show how to solve the learning problem for observable POMDPs by using barycentric spanners to construct a policy cover. In particular, we get an algorithm with quasi-polynomial running time and quasi-polynomial sample complexity for learning gamma observable POMDPs in the standard pack learning model. And we want to emphasize this is the first end-to-end algorithmic guarantee for learning POMDPs without oracles and without strong assumptions about the model dynamics. there is an interesting open question based on the fact that among computationally inefficient algorithms, it is actually possible to achieve polynomial sample complexity. So one might ask, can we achieve the best of both worlds and get quasi-polynomial time and polynomial samples for learning? With that, let me just summarize. So we've seen that modern RL is built on computationally intractable oracles. And one of the thrusts of this work was to go for end-to-end guarantees, particularly in the setting of POM-DPs. And we achieved this by introducing the assumption of observability to the study of POM-DPs. And our key proof technique was exponential filter stability. So that addressed the planning problem, and in follow-up work, we addressed the learning problem, although there is an interesting open question. Thank you for your time.